Yeah, it's recording right now. And the microphone is working, so we should be good. Yes. And I'm noticing that I missed an upload here. I will correct that today. But I've been getting announcements about the selection of the carport. See, nope, got this one here. Timber frame carport with a pitch roof and open sides designed to share to a single vehicle. Then we have J. J is online. You got this one. Jay, is this real or is kind of a render of a kind of design render? It looks very real. Beautiful. Then we have vendor's website. Awesome. Then we have, how do I pronounce it? Hedjet? Hedjet? Hedie? Well, when I see you face to face, I will ask you how it is pronounced. Or maybe you told me I didn't get it, but okay. Very light structure. Metallic more. Okay, nice, Jay. Awesome. Beautiful. Then we have Kai She. No, it's not here. Kai. But look at this one. It doesn't have. Oh, this is a challenging one because it's a cantilever roof. Only hold here. There are no columns. Just wonder the connections here. Kai is logged in. Kai, this is a very challenging design. I was mentioning that you see that there are no columns here. Just wonder how the connections are here. Because there is not even an angle to reinforce that, like in these cases. Okay. Then we have Ritu. She's online. Nice. Vishal, you put your camera unless you want to be. Yeah. Okay, good guy. So Ritu, we have this one. Then Somaye, she's online. Very robust. Very, I always kind of wonder that you have this very robust, but when you see the attachment to the floor, it's just a threaded pin. Well, then this is covered later with something else, but what I mean is that in any accidental Arjuna, in an accidental load application, kind of guard hitting something. So this could be very, very, let's say, fragile. I'm seeing your face, Arjun. You're welcome to join with camera if you want. Then you have the Vrats is not around. Very robust, and also the same thing. Look at the joint, the base. And Umesha is not around. Awesome. Looking good. Similar types, but different, but looking good. Yes, so yeah, they can adjust and level. Yes, yeah, that's a very good point. So yeah, they use these type of connections to the base because they can level the whole, let's say, structure. However, after that, there is something to be done there. That's what I meant. Yeah, good point. Awesome. And the deadline for this was PDF. You're already asking for extension of the deadline until Monday. When was it the deadline? Friday. Yeah, we can do that. Already 2 people have submitted. Right, two people have to meet it. All right. But I didn't consider this. Uh, we had 10 days, 10 for this. So don't get your work, accumulating one big chunk because it's not going to be good. Yeah, we're going to put it for next Monday. Actually, let's do it at once so I don't forget. You see, I always do this. So Monday is, when is it? 17th. I always put that the due date is this, but no, Moodle have a cutoff date, which means that after that, no matter what you do, you cannot submit. I always put the cutoff date, meaning that if by Monday at close to midnight you haven't submitted, I always give chances. Say, well, you know what, you have enough, few hours more to submit that if you just meet the deadline. People are always missing the deadline. So there it is, Monday. Beautiful. Okay, so let me stop sharing. It said that you submitted the when you did that. Was it now? Ah, you put a PDF. All right. You were the one who asked me to do it fancy SolidWork or AutoCAD and everything. You wanted to show off. Yeah, it works. Good. It works. Awesome. You're a show off. Yeah. So, let's go to the lecture. So let's go back to our blockpad friend. Yes. And let me share this one here. And here, put it smaller. Yeah. So this is at a basic level. It doesn't consider all the factors, not yet, all the factors and conditions that we need, but this is the foundation for what we're going to do today. So let's see what we got. Here it is. Awesome. So this is what first we did when we started. So we said, hey, we have this beautiful design and everything. So we said, okay, let's steal a design. So everybody is, I'm going to answer that question soon, Sagar. So far we steal a design from somebody except for Ayush, who created his own. Then you are working in estimating the construction material and pricing. Kind of, see, okay, this is built using, this many beams, material of the beams are this, the columns are this, metallic parts are this. Then this is answering Sayar's question. And so far, you are going to calculate self-weights only, as the document Sagar says it. It doesn't talk about wind, it doesn't talk about snow, it talks about self-weight only. That's it. That's it. If you read in the document that you have to calculate wind or something like that, so let me know because I need to correct that because it's only self-weight and I put it there, document. Check the document. Then we talked about permanent, variable, and accidental actions acting on the structure. But for sure, that's what you're going to do next after this. I'm going to tell you, Sagar, you are in this place. Consider, according to the condition of the location, what are going to be your accidental actions or your variable actions. Variable actions, depending on snow, wind, and then accidental actions, meaning that, hey, a car hit the carport, then you're going to do that. Well, you guys are going to do that. And then we talked last week about how to combine these loads by using standards, meaning that you have usually the component of the, let's say, the permanent actions, you have the component of the variable actions, and then you multiply them by a factor that is going to be a safety factor in the end, And then you are going to sum up both units, and then it's going to tell you your structure is going to be loaded with this. From the top to the bottom, from the sides, and so on. I'm going to prepare an example for that. But today, that's what you're going to do. The last point, or the last 2 points in here, is what you guys have to do next for your carport. Today, we're going to talk about, okay, now that I have those loads, what do I do with them? How do I share them across the members of the structure? Because for sure, this column here is not going to support the whole weight that is going to be applied on the roof, or all the actions applied on the roof. Or one of these beams is not going to be supporting the whole weight. So what do we do that? And it comes a time to talk about tributary areas. This word here. Actually, let me see if I can put this a little bit larger. There it is. If you hear a noise, there is some construction going on here close by. I apologize for that. Well, I cannot do anything about that, but just bear with me. We're going to talk about tributary loads here. And tributary loads answer to the question, what goes to what? So what piece of the action, that sounds funny, what piece of the action goes to each member? And by knowing which piece of the action goes to each member, it allows you to then calculate that member. Dimensions, and basically dimension, because the material you already have there. So which means is that you selected a carport, you estimated the materials, did a pre-calculation of everything, then you added actions on it, but then you are kind of re-verify that what you selected is the correct dimensions, at least that should be there, that is not less. It's not, it shouldn't be more. So that's what you're going to verify. And to talk about tributary areas, for example, when we see this figure, for example, if let's imagine that this is a roof, a concrete roof here. Yeah, a concrete roof that have, and use your imagination to think that this is a perfect square. Yeah, because I have this 10 meters by 10 meters. So imagine that it's a perfect square. The drawing is not, but imagine that. And I have a few beams. I have these beams, and let's call them just beams. Yeah. And this is the top view of this roof, and only seeing the beams. Logically, I will assume that there is a column here, or there are columns in these locations, yeah, that are supporting the beams, and the beams are supporting the roof. And then if I ask, okay, after you have calculated your actions on the roof, say, okay, what load is supporting beam AB, or what load is supporting beam BA, BE, or CF, or this one and this one. And then where it comes the concept of tributary areas. In this case, it's very nice because it's perfectly square, even the drawing is not. But tributary areas, depending on the disposition of beams and columns, can have weird shapes. And then you have to address them as weird shapes, triangular, rhomboidal, and stuff. So in a nutshell, when we talk about the tributary area, is that we say, how can I distribute this surface to each one of those beams? Now, let's talk about just these three beams, beam AD, BE, and CF. Well, if I have the whole weight of the roof of a slab, big, thick slab of concrete, and how should I split it? It's like when you go to a restaurant and then who ate more, who ate less, and then when the bill comes, okay, no, John is going to pay more because he ate more, and then but let's use a name here. Sagar is going to pay less because he didn't eat much, something like that. So in this case, it's a matter of symmetrical distribution of load. So basically, what it does is that the tributary area, which is the area that is only going to be considered to a specific beam or column in this case, or column, for this case, it's going to be something like this. So I'm going to split this in half here. Let me try to do a straight line. I'm going to use, you see that I'm splitting the area that is between beams AD and beams BE. And then I'm going to split the area between these two. What I have done with symmetrically or using symmetry conditions, splitting the areas like this is creating tributary areas. Then we're going to have here is that beam B that is being asked is going to, I'm just picking a color, just bear with me. Here it is. It's going to be subjected to this tributary area, which means that if I could cut the roof in segments, it's like saying, you know what, that beam is going to carry the actions of that segment. So for beam B, that's going to be the load I should use to do the calculations of the beam, dimensions of the geometry of the beam, and so on. What happens with beam AD, for example? Well, the tributary load for beam AD is going to be this one. This, there you have too much space. So what happens with beam CF? You are very smart people. And then you know what's the tributary area for CF. It's the same as AD. So then a few questions appear here. So you say, okay, so it means that the central beam is carrying more weight or more load than beams at the end. Okay, so I have a few options here, a few roads to transit here. So which means that I might increase the geometry, the size of beam BE, so it carries all the weight, and then adjust the geometry of beams AD and CF, so they carry, the load that they should be carrying. That's one thing. And then when you see the distribution of beams, you are going to see beams that are, of larger size than the others. But when you see the designs, most often times, sorry, this is why I draw that. You see that in this case, let me try to draw it. In this case, these beams carry more weight than this beam here, but they are of the same geometry, same size. And why so? Well, it may be, and usually it's often the case, that is, first, it helps you at least accomplish two things. Aesthetically, looks good. You don't want to see different sizes in different parts, just to adjust to the loading of the part. Because for us, if we see same sizes in common areas, we see that is everything nice and is very appealing to the eye. So that is aesthetic factor. And the second factor is that if you are buying material to build this, it means that you can buy the same sizes for your construction members for a wide range of those members that you're going to use, meaning that you're not going to have a bill of material that is going to have very way different sizes. The more variation in geometry you have for your elements that you're going to use in your building process, it takes more time and logistics to organize. And consequence of that, if you buy more members of same size or the quantities increase, then maybe you get a better price for those. So there are different assumptions that say, well, yeah, I can sacrifice using a larger beam for a segment of the roof that is not going to require that much, but I'm going to save money in material. And then I'm going to save headaches in logistics. So that's the main idea here. So this is what we call with tributary areas. Again, this is the most simplest case because what you do is that you look at the geometric, let's say, at the symmetry of the distribution of the load on top of your structure. Now, if I wanted to check, okay, what is the tributary area, for example, for these two beams here, for this one here and this one here? Well, you come here and say, well, my tributary area in that case is going to be, I take a line here, put it in between the two main beams, and then just bear with me. This is not exactly the case, but bear with me. Imagine that there is not this beam B here. Then your tributary area is going to be this one here. All this much. A bit kind of, imagine that the central B beam is not there. So that's going to be your tributary area. Now, complexity can come when you say, you know what, because of the disposition of this, I need to consider this friend something like this. where in reality, the tributary area of the center beam is something like this. So an eye topic, I don't want to, let's do an example about it. So, but the idea, again, the concept behind of tributary areas is that how much of the whole, let's say, weight actions applied to the structure is carrying that piece. It's not that it carries everything. That's the concept of tributary area. And in your designs, now you're seeing, for example, for carports that you selected, you're going to have to decide, okay, how much are the beams carrying? Yeah. And let's imagine that then we say that the tributary areas for the central beam is kind of this much, kind of this, the one that we said. Let's imagine that. We're going to have something like this. Okay? So of course, when I do this tributary area here, it's going to be here and here, it's going to be 5 meters here. And then the length is going to be 10 meters. So that's why I try to, okay, let's use this example like this. So just try imaginary square. And then the floor or roof, let's call it floor or roof, is concrete. I got the density of the concrete there. Then I have the beam here. And then let's assume, just in this case, let's assume that the concrete here, the beams, are simply supported. Yeah, meaning that they could rotate around this point. Let's assume that. Then we have that the floor slab is 5 meters times 10 meters, and the thickness of that is 12 centimeters, 120. Yeah, 12 centimeters. And then you have the dimensions of the section of the beam are these ones. You say, well, how should we proceed? How should we deal with this? Imagine that we cut everything. We said, well, let's cut it here, and then let's calculate let's say the actions applied to the beam, because what I want to do next, kind of as a simple exercise, is to calculate what are the actions applied on the beam, and then what are the reactions that are going to be appearing here, which are going to help me to calculate the columns later. And then also, but I want to check for the deflection of the concrete beam here. Yeah, so let's try to do that. Let's try to do that. So the first thing we do is to calculate the beam self-weight. Yeah, so as we have one beam, so we can do it here. Just let me take a zip of. All right, so let's see how we are. Beam self-weight. I'm going to come here, say, okay, I know that the beam self-weight is going to be the weight of the beam itself only, meaning just this small part here. It doesn't matter the roof, it's just the beam. So they are giving me the density of the concrete there, both roof or floor. And so if I say roof, or just bear with me, it's the same thing, it's the slab. So it's made out of concrete. You have the density. So let's calculate how much is the self weight. Then I'm going to call it that the beam, uppercase, no, self weight is going to be equal to well, if I have a density, kilograms per cubic meter, I need to know the volume of the beam. I multiply the volume of the beam with the densities, give me kilograms. But remember, we don't need kilograms, we need kilonewtons. So we need to multiply that by something to get the kilonewtons. So let's get the volume of the beam. Or I could, volume of the beam. Equal to what? To 0.4 meters times 0.6 meters times 10 meters. There it is. That's the volume of that concrete beam. Awesome. Now that I have the volume, I have the density, can multiply them both, get the kilograms, and then multiply kilograms by, acceleration of gravity, give me weight. So we have that the beam self-weight is going to be the oh no, I have the data there. So my thickness, yeah, that's the thickness of the slab, the whole thing. I'm talking about just the beam. So yeah, it's just the beam, not the slab, just the beam. Yeah. So The beam self-weight is going to be then the density. Where are you, my friend here? Rho times the volume of the beam times gravity. Who is gravity? 9 point, if you want to be exquisite, meters divided by square second 2. Yeah. That's giving me in newtons, but let's put it in kilonewtons. No, kilonewtons. There it is. Why you do me this? Kilonewtons. There it is. 56 kilonewtons. Awesome. I got the beam self-weight. But that beam, as it is expressed right now, is a point load. It's like saying, you know what, the self-weight of the beam, yeah, we can assume, and we will assume at some point in our calculations, that it is a single load point, no? Beam self-weight and something like this. But it is not, the self-weight is not a point load at this point. So it is a distributed load, meaning that if I look at the beam as from its longitudinal axis here, remember the concept of longitudinal axis is the longest axis on the element member, then I would like to know the weight distribution along those 10 meters. Yeah. And to get the load distribution along those 10 meters, what I do is simply divide, call it, of the beam, is divide the beam self-weight by the length of the beam, which is 10 meters. So why is that very nice? Because I could say, you know what? I don't have a beam of 10 meters. I have a beam of 20 meters. So what I do is I multiply of the same material, of the same section, cross section. So what I do is I just multiply those 10 meters times that distributed load represented the self weight and would give you the weight of the whole beam. Yeah. So that's why I put it as distributed load. Nicely here and here. But now let's jump to the slab. Yeah, the floor. So the slab, let's call it slab, is going to be the volume of the slab is going to be the dimension of the slab, the 3 dimensions. It's going to be 5 meters times 10 meters times 0.12 meters. 6 square meters, 6 cubic meters. Now I have the density, and then I repeat the process to get the slab or floor self-weight. Yeah, floor. Then we're going to have the density of it, here it is, times the volume of the slab times acceleration of gravity. Newtons. No. Meters divided by square second to the power of 2. There it is, and let's put it in kilonewtons. There it is. Similarly, we can convert that into a distributed load. And why I would like to do that? Because it is going to act similarly to the self weight of the beam on the beam. That is, I could, if I have not a 10-meter long slab, but I have a 20-meter long slab, if I know the distributed load of that, then I could easily change my calculations. And actually, working with distributed loads is closer to what really is happening in the construction of the whole building. It's not that there is a point load. No. It has a very different behavior in terms of not reactions, but behaviors in terms of what is called bending moments, which is very important for design purposes, and then also in deformation on how it's going to deform. It's very different if you consider only the self weight as a point load than as distributed load. Changes completely. So again, to transform the floor self weight into a distributed load, if I'm interested in the longitudinal axis of the beam, then I need to divide here. I will divide. I have the, let me put it down so it doesn't bother that much. Let's call it W of the floor. Then I'm going to talk the floor self weight divided by 10 meters. There it is. 14.26. About 3 times the weight of the distributed load of the beam alone. See when you compare these two values. Now, what do I do with this? Let me put bolded. I can combine them both to say, you know what, the total of this snapshot I'm taking, distributed, is going to be the sum of both. So I can call it W total equal to my friend the beam plus the floor. There it is. Again, this is not being affected by any of the multipliers appearing on the standards, but we will talk about that in another exercise. But this is the pure load applied there. Yeah. And how it looks like if I bring a beam, kind of how does it is depicted? Well, I have A and B, and I have the whole distributed load applied to the distributed load, which corresponds to this one. And then I'm going to have a couple of reactions that are going to be transmitted to the columns. Yeah. So the load path is going to go from the floor to this side, and then to the columns, and then to the ground. But we are at this stage only. We're just taking a look at the beam. So now that I have that, I can calculate the reactions of that, isn't it? Because now I'm looking at this floor beam group from this side like this, something like this. So that, and everything is represented as a distributed load. So then I can calculate the reactions here. So how can I do that? How can I calculate these reactions there? Well, it's very simple. This is very symmetric. So if it's very symmetric, it means that I could just split the reaction into two. The reactions are going to be exactly the same in both cases. Yeah. However, when you look at the type of geometry here, that depending on the construction, the tributary areas might change, and then one end could be more loaded than the other, then you really need to calculate what are the reactions in each one of those cases. Not in this case, because this is a very simple example. So how much is the reaction here? Okay, let's call it reaction in A, reaction in B, only vertical. We're not going to talk about horizontal reactions, even though we would need to check for horizontal reactions. Not thanks, but due to actions applied in the horizontal axis. For me, horizontal is like this. But let's talk about vertical reactions only in this case. Then I will go, okay, now the reaction in A is going to be equal to what? Well, it's going to be equal to the distributed load applied on the beam times the length of the whole group, the beam, divided by 2, because that's what it says. Is very, very simple. Times 10 meters divided by 2. And then as mentioned, let me just out of the view so it looks better. Then the reaction in B is just the same. I can put it, it's equal to this. That it is. So I have calculated the reactions in both supports. Well, calculated the distributed load by taking into account the geometry and density of the materials. Then I calculated the reaction forces here, and then I want to take a look at how this is going to deflect the deformation of it. We don't need to do any big calculations. We can say, you know what, we can go to tables already that are proven that says how much is the deformation for your loading case. So in this time, if we have a simply supported beam with a distributed load on top of it, we're talking about this case. Typically, how it would go, I believe you're taking a look at this now, is that you build the loading function, then you integrate that loading function, but you take the derivative of that loading function to get the shear force function, and then you take the derivative of that to get what is called I believe the other way around, the bending moment function, and then I believe it's integral, and then you integrate again, and then you get what is called the slope function, which tells you, the angles in the deformation process of the beam, and then you integrate again and get the deformation, how high, how big is the deformation here. But this is given to us on a silver plate, and we did not need to do anything. And if you put your nose very close to the screen, you're going to see that this is the one I need to use. I have a distributed load, W. You see, it is it simply support the beam. And it tells you, hey, if you want to know what's the maximum shear force, well, this is the way you have to do it across the section. But if you want to know what is the maximum deformation that is going to happen at half of the beam, and it happens at half of the beam because it's symmetric, then you're going to have that this is the formula you need to use to calculate the maximum deformation. So let's take a look at this. Doesn't move. Here it is. All right, so I have this. Can I put it a little bit smaller? Here it is. I have the modulus of elasticity of the concrete. The concrete modulus of elasticity of the concrete ranges from 20 something to 40 something. So it has a large variation, and it depends on the type of concrete you are using. I just picked this one, okay? It's not like in the case of your exercises, strength of material for steel, that tells you A36, that's a fixed, let's say, modulus of elasticity. That is not that John is going to have one value and some other is going to have no, it's just one single value. But for concrete, depending on the composition of it, it's going to vary. For this case, I just picked this number that is within the range. Now, I know that the deflection calculation is, let me just write down the formula so we can have it. And actually, I could just leave this larger. I'm going to write down the formula here. So it's going to be that Y max is going to be equal to 5 times W times L to the power of 4 divided by 384 times E times I. But then I need to close this down here and close this down here. There it is. There it is. So it says that if I want to calculate the maximum deformation of the beam, the concrete beam, I need to know the distributed load, the length, then the modulus of elasticity that is given there. So I have the length, I have the distributed load W, I have the modulus of elasticity, but I do not have the moment of inertia, which I need to calculate. But luckily, the moment of inertia of a square or rectangular section is very easy to calculate. It's a formula that many people know already by hand, by heart, in the sense that you don't have to calculate anything kind of complex like that. So I have it here. Let's put it on the top. I equals to what? So it's going to be the base times the height, base to the power of 3 times the height divided by 12. That is, the base is 0.4, and I'm going to write here 0.4 meters to the power of 3 times the height, 0.6 meters, and this is divided by 12. There it is. Base cubic of that to the power of 3, and then times height divided by 12. Which means now that I can calculate the maximum deformation of the concrete beam according to the loading. And let's see how it goes. So we're going to have that Y max. It's going to be the question I had there. It's going to be 5 times the distributed load that I called it WT times the length of the beam to the power of 4, and the length of the beam is 10 meters. And this is going to be divided by 384 times E times I. Giving me a weird unit there, but it's because I'm not telling it which unit I need. So you know what? I want to know the unit, but I want to know it in millimeters. Yeah. There it is. Beautiful. Mm-hmm. This is according to this. So 5 times the distributed load times the length, power of 4 divided by that. So it's 5 millimeters too much, too little? Well, everything depends on what is the the recommendations for maximum deformation in this type of structure for this type of material. Look a little bit high. It just, oh, look at this. I think this is correct one. I'm amazed about this program. Sometimes I try to do it by the book, but no, it's 5.50 millimeters. Just a rudimentary test I did here. Wow. Yes, let me put it because I just want to make sure that this is. One should always check the. Mhm. Oh, I messed it up now. Yeah, 5 millimeters, 5.50 millimeters. So it means that you took your design, your carport, found the tributary areas, converted the self weight in this case, and then if you have any other variable actions uh, or applied actions that you need to take into consideration, you transform them into distributed load, at least for this case. Then you start kind of looking at each individual member from that point of view for designing purposes. In this case, for concrete structure, it is not just it's not going to resist the load. It is not that it's not going to deform because some of you already working with this in this area know that concrete is not very amicable for tensile stresses. It just snaps. That's why you put some bars inside. But a compressive stress, the concrete says welcome. But that's why when you have a maximum deformation of this corresponds to a maximum bending moment. And the bending moment, if you wanted to go to know that, well, is not here, but you could find it. And with that bending moment, you can calculate the stresses applied to it, and you can see if that tensile stress produced due to the load and the deformation is going to create is larger than the value that you need to have, or the strength corresponding to the concrete, by remember applying a comparison method. Remember that when we talked last class that sometimes the comparison is not only one-to-one, not only time, but there are methods that is one-to-one, but there we got it. Awesome. Now, what happens with the beam with three supports? And what is the beam? This one here. So again, I have a tributary area, and let's imagine that we don't have this beam BE, just to make things more drastic. So the tributary area is going to be, again, kind of the same or very similar to the one that we use for BE, because it's going to be the one that I have here. It's going to be this one here. So it's going to be very, very similar. So the distributed load of that beam is going to be very similar to the one what we did because of the symmetry that I obligatorily put in the problem. So we can assume that this distributed load is going to be the same for the three support beam. But the difference with that is that the three support beams are statically indeterminate. And again, repeating the things that we said last hour is that they are statically indeterminate because there are more restrictions that I need to support the beam. So meaning there are more restrictions that I need to guarantee the staticity of the element. Meaning that with two supports, they do it, but I'm putting a middle support because of stiffness requirements. So if I'm putting more, I will check. I have a question. Okay. So if I put more supports, meaning I'm over restricting the beam, which means that the equilibrium conditions are not enough to solve the problem. So I need to use other methods like the three-moment method, conjugate method, superposition methods. There are several methods to do it. But locally for typical cases, there are tables. Let's see the comment from Jay. Jay said, I think we get different value in MOE maximum. What is MOE? What is the MOE? The maximum deflection, you mean? Ah, moment of inertia. How much you get? How much are you getting? Are you considering only the beam or you are considering the whole slab plus beam group? You cannot mute yourself if you want to talk and it's easier for you. Would it be that happens the same? I need to check this. That happens the same as this one here? Would it be? This is something. All right. Yeah, let me check. Just, I'm having the calculator here. You're not seeing it, but, it's just, 0.4 times 0.4 times 0.4 times 0.6 divided by 12. Yeah, you are correct. My bad. What weird thing is happening here? I need to find out the mathematics behind, not the mathematics, but how the software takes this. Thank you, Jay. Good comment, good catch. Yep, use parentheses. Wow, 32 millimeters. That's a lot. That is a lot for a concrete beam. What, 10 meters span? Oh, I need to check that. Wow. Good comment, good catch. To make some tests with these units. Just let me just take your time a little bit. So 4 times, because I assume that this is what's happening. So this, I think it is just it is just taking the last one and no, it's not. I don't know what it's doing, the software. Ah, 12. Yeah. Wow. You know, if this didn't happen, I wouldn't notice this. I was blindly trusting the process. Wow. Thank you, my friend. Very good. Very good catch. So it doesn't do anything if I just apply power to the unit. Okay, good. Thank you. So and just buffer. But so when we have this, then, and we have a distributed load on a simply supported, well, not simply, a supported beam by three simple supports, then there's a typical construction, which means that we can right away decide, okay, what's going to be the maximum moment, what's going to be the maximum deformation. And also in this case, the maximum deformation is going to happen not even at half of the span between two supports. It's going to be at a weird distance of 0.4. How much is it? 4 to 15. Imagine that. But I get to know how much is the reactions. Let's see. Let's calculate the reactions in 1, 2, and 3. Reactions in 1, the reaction in 1 equals to the reaction in 3. If you see that the shear force diagram there, clearly states that the maximum reaction is going to be in the center. Yeah. So reaction 1 is going to be equal to 3 times the distributed load. We said we're going to use the same, times the length of that section. And the length of that section for us is going to be 5 meters. There it is. But we also said that, you know what? One is going to be equal to the other end. Why are you doing this? Because there it is. But the reaction in the middle using the tables, we don't need to use any integration mathematical method because this is a typical case, and that's why we can do it. It's going to be then this 10 times the distributed load times L, which is again is not the span of the section, which is symmetric. So see, there is a symmetry there, so it's going to be the same L divided by 8. Yes, I think did I get it correct? No, that it is. Just checking the formulas. So imagine that in this case, the column that is going to be located in the middle of that concrete beam has to support how many? How much more? 120, but 400% more load than the ones at the end. And it's the very same beam. Mm. If we want to calculate the maximum deformation, then I can say, let's use the same nomenclature that they have here, this delta max, just not to mix up with the other one, to follow the same ones in the table. So delta max, didn't do it. It's going to be equal to W, so the length, the distributed load, times the length to the power of 4 divided by 35 times E times, let's keep using the same one. There it is. And let's put it in millimeters. So look at this now. This is also, now kind of I'm doubting myself about the operations, but no, let's trust this is okay. So what's happening here is the following. You see that if I consider this to be the same beam, but the beam I attached it with just 2 supports, the deformation of that beam under the same distributed load is going to be 32 millimeters, which can be, not good. I don't think that's good. For concrete, it's not good. For steel is another story, but for concrete, it's not good. But if somebody comes and says, well, but what about if we put some support in the middle so we restrict a little bit this? Well, if you put a support in the middle and restrict that, then the maximum deformation that you're going to get, and you're going to get it at max location, is going to be at 0.4215 times 5 meters at 2.1 meters from the ends. And the deformation is only going to be less than a millimeter. So, which means you killed all the problems you have. So, meaning that, well, I didn't need to increase the size of the section of the concrete beam to reduce the deformation, because remember that if I increase the size of the section, what I'm doing is I'm increasing the moment of inertia of the section. Remember that we understand formulas. Formulas can help us decide what to do. So if I increase the I, which is the moment of inertia, by increasing the dimensions of the section, then the deformation is going to be less. But I could put a support in the middle, and then this is what's going to happen. That the deformation is going to be drastically reduced to less than a millimeter, which is awesome. This is a beautiful sequence of operations here. Oh, this is annoying. And with this, let's close it today. But this is also kind of going to come to the third part of the design that you're doing. Yeah, calculation of the tributary areas, and then simple calculations of the beams and stuff. And we will touch on the columns and all of that. Yeah? But we will put a little bit of more standard, nomenclature here and stuff. Do you have any questions about it, about this? Thank you again, Jay. Big appreciation to what you noticed. And also to all you guys who commented. You make the class very engaging and very interactive. By the way, guys, I don't say this very often, but for the first meeting we had, we met last week, You are a very good group. You are a very good, let's say, pack. I look forward to working with you. Keep going like that. So let's leave it until here. And any questions? Send me an email or something like that. Let's connect. And I will upload this PDF also to Moodle. You're going to have access. Hope to do it within today. And then thanks again. And remember, I want to put it also in the announcement, but next week is not face to face, but it's going to be online. Kai, do we have any homework of the lecture? You will have. You will have. Because but you're still working on the well, I don't know if you were one of the ones who finished it yet, but you will have because there is a homework going right now. But not like evaluated exercises. It's going to be like a design process. So not rush. Online lectures are pretty good. Thank you, Jay. I believe you're encouraging to have more online lectures instead of face to face, but the ones that we're going to have face to face is because it's on Monday and you guys are going to have Mondays, at least some of you. But why not? So one of these Mondays we can switch to online. Why not? We can agree on that. But anyway, thank you again. Take care. See you next week online, and have a beautiful weekend. Enjoy the dark times. Bye. And to stop this now here.